Greetings and welcome to the introduction to astronomy. In this lecture, we are going to look at the distribution of galaxies in the universe. So how are galaxies distributed across our universe? And we could think about how they are distributed in space. So are they isolated? Are they in groups? If they're in groups, are they large or small groups? And these are the kind of things we're going to want to look at. But first we want to talk about what we call the cosmological principle. This allows us to study the universe. Early observations by Hubble said that there were approximately the same number of galaxies in each direction. And the cosmological principle states that the universe is isotropic and homogeneous. What does this mean? Well, isotropic means that it looks the same in all directions. So no matter what direction of the sky you look at, you would see roughly the same number and types of galaxies. It's also considered to be homogeneous. So every very large volume of space looks essentially the same. Now we're talking about tremendous volumes of space there, not just around galaxies, but around massive galaxy clusters and filaments of galaxies that we will look at. So let's start off looking at nearby galaxies, and that would be our local group, which is our local cluster of galaxies containing about 50 galaxies or so. It has three large spiral galaxies. That includes our Milky Way, the Andromeda galaxy, as well as another satellite galaxy with Andromeda known as M33, or the Triangulum galaxy. We are still learning about these galaxies. There are many dwarf ellipticals and irregulars, and we can see those here. We have the yellow, or the three primary spiral galaxies there. There are elliptical galaxies and irregular galaxies in the red and blue. We are still discovering new members of our local group. Now remember, this happened when we talked about stars as well. We were still discovering brown dwarf stars around our solar neighborhood. Well, here we are discovering new galaxies even within our own local group of galaxies. So there are, through automated surveys, we see very faint galaxies that are only now being detected. And these are important because they were predicted by formation models. So they were thought to be there, but had never been detected until recent automated surveys were able to pick them up from the background of stars. Now this is a relatively small cluster. There are much larger clusters as well. A nearby one is the Virgo cluster, which is the nearest large galaxy cluster, including the giant elliptical galaxy M87. This one contains thousands of galaxies and is about 50 million light years away on average. We can see even larger clusters such as the Coma cluster. And that is also dominated by the elliptical galaxies. And it's much larger, containing tens of thousands of galaxies, and is 250 million light years away. So clusters get very, very large, and we're going to see even larger structures as we continue. But what about the distribution of galaxies within clusters? Well, we have social and antisocial galaxies, or at least social galaxies and shy galaxies. The elliptical galaxies are social. They are found in the crowded centers of clusters, whereas spiral galaxies tend to be the shy ones, found isolated in the outskirts of the cluster. Now, why might this be the case? Well, it's thought that collisions would be less likely to destroy a spiral galaxy far away. There'd be far fewer collisions for a galaxy on the outskirts of the cluster, so that the spiral structure would remain. Galaxies toward the inner part would undergo lots more collisions and would convert to an elliptical type galaxy. Now we can also learn about galaxies through gravitational lensing. Gravitational lensing is a prediction of general relativity. And if you remember, we've looked at this previously. Mass will bend space-time and deviates the path of light. And that means we will get multiple images of these distant objects. The distant galaxy images are distorted. So as light passes by from a distant galaxy here, the light gets curved and bent so that it looks like it's coming from a different position. And what we will see is, even though this galaxy is directly behind, we see the foreground galaxy here, but we may get multiple images of the background galaxy as well. So we can see multiple images of this background galaxy. The mass that we see when this happens includes dark matter. So the amount of bending depends not only on the visible matter, but also on the unseen dark matter. Now we can look at an example of this here. And here we see a lensing by a galaxy cluster. And the arcs that you see circled here in each of these circles are regions of where the lensing has occurred from a distant galaxy behind, and it has been stretched into arcs that are visible here. Now here is one image that we see. Let's take a look at another one where we can see this in a little bit more detail. And here we can see great arcs of material where this has been, where the light has been stretched by the cluster's gravity. So as the light from a very distant galaxy passes through, it gets completely distorted by the gravitational lensing here. Now, what about structures beyond the galaxy clusters? Well, clusters also cluster, and clusters become in even larger structures called a supercluster. And we get gaps between the superclusters that we call voids. So here we see a simulation done of the universe. So the initial spot blast there, and how everything collapses into clusters and filaments of galaxies. So the galaxies fill a very small portion of the actual space. Most of space is actually contained in these voids, which have few galaxies at all. Now we can also look at this in another. This is a simulation. What does it look like in real life? Well, we can make redshift surveys that allow us to determine distances to galaxies. We find that galaxies are concentrated into filaments and empty voids. So here we see some of those. The darker areas are areas of galaxies, and there are also large voids, regions where there are no galaxies, or at least very few galaxies in this. And what we find is that 90% of the galaxies fill only 10% of the universe, meaning, as we looked at early in this class, the vast majority of the universe is very, very empty. Now, as we continue to map the universe, we can look at a little more detail here, where we see a number of these clusters of galaxies put together. So here is an image that we see. This is a whole sky image. There is our Milky Way at the center. And looking around that, we can see all of these other different clusters. And here we note a few nearby objects, such as the molecular cloud, but also a number of clusters, such as the Fornax cluster at 20 megaparsecs, and other clusters at even greater distances, given by their redshift. So this Fornax cluster and Virgo cluster would be relatively close. Some of these superclusters are even much, much farther away. But we do start to see again how everything is concentrated into these filamentary structures throughout the universe. So let's go ahead and finish up with our summary. So what we've seen is that galaxies will group into clusters. Those group into superclusters, which then become the filaments, and the empty spaces between them become the vast empty voids between these filaments. We also looked at the cosmological principle, which states that on the very largest scales, the universe is homogeneous and isotropic. Homogeneous, every large section of the universe looks the same. Isotropic, the universe looks the same in all directions. So that concludes this lecture on the distribution of galaxies. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.